Hello and good afternoon, CTS265 Section 840 students for the Fall 2015 semester at Anne Arundel Community College. This is the CCNP ROUTev7 Course, and today's video tutorial is going to be on Cisco Networking Academy Lab 3-1, where we're going to be taking a deep dive look at OSPF Virtual Links. And so for those of you familiar with the lab, I have already configured all the IP addressing, and we're going to dive in right here at step 2. So typically starting off with step 2, we'll be on router 1. We'll go from user exec to privilege exec and then into global config. Now, excuse me, we're being asked to create OSPF process 1 and the OSPF router ID on all 3 routers. So it says using the network command, configure the subnet of the serial link between router 1 and router 2, as well as adding loopback 1 on router 1 and loopback 2 on router 2 into OSPF area 0. Now there's a couple of ways that we could do this. I'm going to go ahead first and say router OSPF 1, and now that I'm in the router OSPF 1 section, you can see we have all kinds of different options that we can select. So the first thing I want to do is I want to set the router ID. Now what's interesting here in the lab, and we saw this on Monday night, is when I type in router ID 1.1.1.1 on router 1, you'll notice I don't get a message here telling me you need to clear the OSPF process or reload the router, which is typically what you would need to do when you change the router ID if and only if I already have an adjacency established. So with no adjacency established right now, I can change the router ID to 1.1.1.2 or 3, or I can keep changing it. And you'll notice it's not prompting me to clear the OSPF process. Now the reason for this is because there's no adjacency formed yet. So there's no harm in me making this change right now and basically saying, you know, hey, I'm not really sure what I want the router ID to be, and I'm going to go ahead and reset it a whole bunch of times. But then as soon as I have an adjacency established with an OSPF neighbor, that is when changing the router ID is going to require that I do the clear IP OSPF proc or process in order to get that change to take effect, because that is going to actually change the link state database significantly, because all of, in this case, router 1's advertisements, if we're not using 1.1.1.1, the link state ID is going to change throughout the OSPF domain, and we need to make sure we take that into account. So let's go ahead and set the router ID back to 1.1.1.1. If I do show IP OSPF, or I'm sorry, do show IP protocols, you can see that we have OSPF area 1 here, and the router ID is simply 1.1.1.1. And again, had I changed it to 1.1.1.5, it would show up as 1.1.1.5. Again, not prompting me to reset anything or to clear the OSPF process, because at this point we haven't established the adjacency yet between router 1 and router 2. Now the next step, I'll say do show IP interface brief. The next step is asking us to enable OSPF on not only the transit network, this 10.1.12.1, but also on the loopback interface, 10.1.1.1, loopback 1. Now it wants us to use the network statement, so we'll start out, we're going to do a mix and match here to see that we can do this differently, or do it in a multitude of ways. So I'll do the transit network, we'll say 10.1.12.0, and I'll use the wildcard mask of 0.0.0.255, and these need to be in area 0. Now when I say do show IP OSPF protocols, or I'm sorry, interfaces, right, you can see that it's up and running on serial 000. Now how did we activate this on serial 000? Well, all I need to come down here and look at is attached via the network statement, right? This is a point-to-point connection, which means there will be no DR BDR election. What is my cost? My cost is 64, and 64 is the default cost for a T1, and we're going to talk about the auto cost reference bandwidth here shortly. So let's clear the screen here. You can see we've got our hello and dead and wait timers, right? The hello is 10, the dead is 40, and remember, typically the hello time is 4 times the dead time. The only time where the hello is not, I'm sorry, the dead time is 4 times the hello time. The only time that the dead time is not 4 times the hello time is when you manually configure both the hello and the dead time, right? So I could set my hello time to 5 and set my dead time to 12, and therefore it's not 4 times. However, if I only set the hello time, then OSPF will automatically configure the dead time to be 4 times whatever I set the hello time to. Okay, so let's go ahead and drive on here. So this is the first way we can activate it on or get the OSPF process to be running on an interface is via the network statement. So if I say do show run section, let's pipe it to section OSPF, what do we get here? Well, you can see that we've got the router ID statement and the network statement. Well, for the loopback address, I'm actually going to go ahead and go into interface loopback 1. Let's say do show run interface loopback 1. And this is my engineering, this is a loopback that is simulating an engineering network here. Engineering department network interface off of this router. All right, so let me now go ahead and say IP OSPF1, excuse me, area 0. And so this is the other way that you can activate the OSPF process on an interface. So if I were to say do show IP OSPF interface brief, you can see that we now have the loopback interface 1, process ID 1 area 0, now running with a cost of 1 because it's a loopback interface. And this is a point-to-point connection. And you can see we've got no neighbors on any of those interfaces right now. Okay, so we've got router 1 configured so far. Let's change, and then they wanted to mention, it's interesting, so when you see the OSPF networks, or the loopback interfaces in OSPF networks, are by default advertised as /32s, as stubs, as /32s. So, however, we can change that by saying IP OSPF network point to point. And that'll make sure that it gets advertised as a /24, which is actually what that loopback interface is originally configured to be. So we'll go ahead and type in, we'll say write mem, and let's walk through a couple commands here. So show IP protocols, right? This is going to give us our router ID, and as you see, it looks like I left it. Did I actually leave it at 1.1.1.5? Let me check that really quick here. Show run section OSPF. I did. All right. So still, if what I said earlier is correct, let's check it out. OSPF 1, router ID 1.1.1.1, and again, no adjacency. So did it ask me to clear the IP OSPF process? Absolutely not. So now let's save this off, and let's dig back into our confirmation commands here with the show IP protocols. So we'll say show IP protocols, and there we go. Now we've got the correct router ID. So again, what we're able to see here is the router ID is 1.1.1.1, and I'm routing for excuse me, routing for network 10.1.12.0 here in area 0. And again, this is routing for networks and then routing on interfaces configured explicitly. And the reason that it says loopback 1 here is because, remember, we explicitly configured OSPF on the loopback 1 interface. If I were to go back into global config and go into interface serial 000 and say IP OSPF 1 area 0, what do you think that would say? So do show IP protocols. And it still says routing for networks, and now it shows it that it's explicitly configured there. So if I say do show IP OSPF interface brief, sorry, OSPF interface was what I was looking for there. We now come in and take a look. It's interesting that the IP protocols picked up on the change, that it was explicitly configured under the interface, but show IP OSPF interfaces still says it's attached via the network statement there, and on loopback 0, it's the interface config. So that's interesting. So again, show IP OSPF interface says, hey, it's attached via a network statement for serial 000. But when we ran the command do show IP protocols, what does it show? It says routing on interfaces configured explicitly, and it added in serial 000. So if I say no IP OSPF1 area 0, and I say do show IP protocols, we would expect to see that serial excuse me, we would expect to see that serial 000 is gone, and it is from the routing on interfaces configured explicitly. So interesting output, and this is 15.3 code, as you can see here. These are actual Cisco 1841 routers, all running 15.3.3xb12. And again, very interesting behavior that show IP protocols picks it up that it's on the interface. However, the show IP OSPF interface command doesn't update. It still has it locked in there with the network statement. So the next thing they ask you to do is to clear the IP OSPF process. However, that's not needed because show IP, and actually we have it right here above us, this router ID, we are set to 1.1.1.1. So let's jump over to router 2. And let's do some configuration work on router 2 here, and we're going to actually look at what happens before we set the router ID. And we'll see how OSPF grabs its interface. So if I say show, or how it grabs its router ID, show IP interface brief, you can see that we have a single loopback address, loopback 2, and its IP is 10.1.2.1. Now, when we compare this IP address to these two IP addresses here, you can clearly see that this address is less than both that one and that one. However, it is a loopback address, this 10.1.2.1. So even though it's the lowest numbered from an IP address perspective, the lowest IP address, numerically, it is a loopback address. And so OSPF is going to select its router ID based off the same three criteria EIGRP uses, number one being the router ID statement that we configure under the OSPF configuration. The second criteria, if there is no router ID configured, it's going to grab the highest loopback address. And then if there's no loopback addresses configured, it's going to hit down to criteria number 3, which is the highest IP on a physical address. All right. And if you don't have any IPs configured at all, it's going to come back and tell you, as we saw in one of the discovery activities, that I'm sorry, I'm unable to start OSPF. All right, so on router 2 here, we're going to go into global config, and I'll simply say router OSPF 1. Now, you'll notice we don't get, it's not barking at us or complaining with a syslog message that the router ID is not set. Because again, just because I haven't typed in router ID does not mean it hasn't selected a router ID. If I say do show IP protocols, what should the router ID be? Well, based off the 3 criteria we just talked about, or the 3-step process, it's going to grab that highest numbered loopback interface, and highest number being the highest IP address, which it did, and this is loopback 2, right? So that's what it's selected as the router ID. And so here again, it's interesting that they ask you to set the router ID. So we'll set it to 2.2.2.2 for router 2. Remember, the router ID is not an IP address. It takes the form of the 32-bit dotted decimal notation IPv4 address, but this is not an IPv4 address. So I can't say do ping 2.2.2.2 and expect to get an answer back. Now, I can certainly configure this as a loopback or maybe throw it onto a physical interface. However, keep in mind that if that's not what you've done, that when I set the router ID, it is not an IP address, right? So we're not going to be able to ping it. Now here's what's interesting. When I say do show IP protocols, what is the router ID now? Exactly, and we haven't had to do the clear IP OSPF process because, again, the router ID has been set. So what if I were to say no router ID 2.2.2.2, right? Do show IP protocols. What's the router ID going to be now? Well, it goes right back to the 10.1.2.1, which is originally what it was set to. So let's do this so that we can see this clear IP OSPF process command in play. We're not going to set the router ID right now, and this is where the lab, it looks like an order of operations issue on the lab where they overlook the fact that you must have the adjacency up first, or else that clear IP OSPF proc doesn't need to be run. So we've got our router OSPF 1. We're in the router configuration area. We'll go half and half here again. So do show IP interface brief. So let's go ahead and get OSPF up and running here on network. We'll use 10.1.12.0, 0.0.0.255. And we'll say area 0. We should see an adjacency come up immediately. There we go. That's fantastic. And we also want to enable it on, and they're going to hold off on that other serial interface. They want us to drop it onto the loopback address. So interface loopback 2, and I'll say IP OSPF 1 area 0 for the loopback address. Now, when I say do show IP OSPF interfaces, you can see that we have our two interfaces here again. And how are they configured? Well, the loopback interface we did specifically with the interface enable command, which was that IP OSPF 1 area 0. And then how did we enable OSPF on the serial interface? Exactly. We went ahead and configured the network statement under the OSPF config section of 10.1.12.0 with the wildcard mask of 0.0.0.255. And then we said area, and I'm running way out of space here, area 0, right? And then we have the cost, right? The OSPF cost of each of these links. And so the loopback address has a cost of 1. A serial T1 interface has a cost of 64, right? Okay. Let's see here. Let me do a quick check, and you can see that we are showing that our neighbor count is 1, and we're adjacent with neighbor 1.1.1.1. Again, the router ID being used to tell me who I'm adjacent with. And I think that is it. So you can see what's our router ID here for router. Oh, I'm sorry, that's process ID, router ID 10.1. Yeah, this is router 2. Yeah, this is router 2's loopback. So we're going to resolve this issue right now. So the router ID for router 2 is 10.1.2.1, which is this loopback 2, because again, remember, we pulled off the router ID statement because this is what we want to see. We want to see what happens now that an adjacency has been formed. Do show IP OSPF neighbors. So I'm adjacent with router 1, and let me see if I can get us some additional real estate here. Try to get that all on one line. There we go. So I'm adjacent with router 1. Now, this is different than anything we've seen so far, right? When we looked at the discovery activities, the state, we're fully adjacent. However, what is that? It's just this dash, right? What does that mean? Well, the state setting and the priority setting are inextricably linked here and helping us understand what's going on. Remember, when the priority of 0 is set, and by default on point-to-point links it will be set to 0, there is no DR or BDR election that takes place. So as a result, we just get this dash. Because again, if you think about it, it makes sense. We're talking about, and actually I don't even need to draw it right there. If I were to go ahead and come over here, if you think about it, it makes sense, right? So we've got, let's get the drawing tool up here, and it makes sense, right? So we have the interface here, and we've got the interface here. How many routers are going to be on this point-to-point link that runs between router 1 and router 2. There's only ever going to be 2, right? So do I need to have a DR and a BDR configured? And the answer is no, right? We don't need that. There will be no DR and no BDR. The priority will be set to 0, okay? And that is exactly what we're seeing over here, is our priority gets set to 0 by default. And then we just get the dash sign here saying, hey, there is no DR, there is no BDR, there's not going to be any druther relationships or adjacencies, because again, this is a point-to-point link, right? There will only ever be 2 routers on that link. Okay, and we're familiar with the dead time. It counts down from 40, and every 10 seconds it'll refresh, so we should never see that drop below 30. And then this is the IP address of the neighbor, not the router ID of the neighbor. The neighbor ID is the neighbor's router ID. This is the IP address of the neighbor, and this is the interface out which, my local interface, out which I've established this adjacency with router 1. So let me clear the screen here. We'll clear the screen here, and we're going to go ahead and deal with the router ID right now, because remember, the router ID is still set to do show IP protocols. It's still set to 10.1.2.1, and we want to change that. And we want to see what it looks like when we have to clear the process. So router OSPF 1, router ID 2.2.2.2, and now we get the command reload or use clear IP OSPF process for this to take effect. Now, why do we have to clear the process? Well, again, remember, the router ID in OSPF plays an enormously critical role in the link state database formation and being able to do the recursion and identifying the nodes in the OSPF graph. And so now that an adjacency has been formed, if I were to say, if I come over here to router 1, let's say do show IP OSPF database. Let's take a look at it. So here's the database. There's not much going on, right? We've only got type 1 LSAs. So these are my type 1 router LSAs. But again, how are the routers identified in the link state database? They are identified by the router ID. And the link state ID, right? That's what this column is here. This is the link state ID. For the type 1 LSA, the link state ID is the router ID. Okay? These are in fact, both of these columns are the router ID, as you can clearly see. These are not IPv4 addresses. They are 32-bit dotted decimal notation values being used to represent the router ID of the router in question. So this one here is for router 1, and this is for router 2. Now, it just so happens that right now that is an IPv4 address on router 2, right? But these values are not IPv4 addresses. All right, and then we've got our link state age, we've got the link count, the checksum, and the sequence numbers. You can see not much activity, right? 0, 2. And again, sort of to repeat, you can see that this is a pretty large number here, and the best example and analogy I can give you is that if there were to be a change to this database every 5 seconds, it would take 600 years before this number rolled back over to 800000001, which is where it starts. So I think it's pretty safe to assume that even in that linear fashion where it's incrementing here 03, 04, 05, 06, and just continuing to count up and up and up in hexadecimal, that it will take 600 years before this number rolls over again. So chances are you're not going to run into any problems with the link state database, and if you did 600 years later, and that is definitely some serious return on investment for your hardware, you're not going to be the administrator at that time, so you don't need to worry about that. All right, so let me go ahead and clear the screen here. And let's go back to router 2, and let's pick up where we left off, where we set the router ID, and now we want to say do clear IP OSPF proc, stands for process, and it's going to say reset all OSPF processes. There's no way for me to pick a single process, right? It's all or nothing here. And I'm going to say yes. Now you're going to see the adjacency go down because, again, it has to tear the adjacency down and then it has to bring the adjacency back. And the reason for that is when I say do show IP OSPF database now, what has happened to the router ID? It has changed, right? And this is critical. This is why we need to do the clear IP OSPF process after the adjacency has formed if we change the link state ID. And you can see, not the link state ID, the router ID. And you can see here that for router 2, we've set ourselves back all the way to 1. This is the first update, right? So the first sequence number will always start at 800001. And you can see we've had a new change here, which was we updated the router ID on router 2, and that has caused our sequence number here on router 1 to increment. Okay, so that's an explanation as to why you need to do that clear IP OSPF. Let's take a look now on router 1. It wants us to come back to router 1 and say do show IP route. And you can see that we're only learning right now a single OSPF route here, right? 10121, and that is loopback 2 on router 2. Now, what's interesting here is we have a cost of 65, right? Now, remember earlier we looked at the loopback and it said metric 60. I'm sorry, we looked at the transit network. In fact, let me pull that off. We looked at the transit network and it said that the T1 had a cost of 64 and the loopback had a cost of 1. So our total metric to get to that loopback is 65, right? And that's how that number is being calculated. Again, the administrative distance of OSPF is 110 as opposed to EIGRP, which is 90, and then via, right? So from router 1's perspective, who am I learning this information from and who am I going to get to that destination? It's going to be 10.1.12.2. That's router 2. And out what interface am I going to go to get there? It's going to be serial 000. And this is how long the adjacency's been up, is 1 minute and 3 seconds, because remember we did that clear IP OSPF process which reset our adjacency. So if I were to say do show IP OSPF neighbor, we're going to see much of the same, right? And there's that dead time. Let's watch the dead time as it gets closer to 30, and then we'll catch it back at 39 right there. So it goes to 30, then every 10 seconds we've got hello packets coming in. So if I were to say do debug IP OSPF packet hello, I believe, or hello. There we go. So what we're going to see here is every 10 seconds we're going to be sending and receiving hello messages. And so you can see right here, we received a hello from who? Well, 2.2.2.2, and then it moved. So where are we sending the hello packets? And I'll let this go for a second here. Let me clear the screen and then we'll kill this. So this is some really good output here, right? So we're receiving hellos from 2.2.2.2, and we know that this is router 2 based off our router ID. Now we're also sending hello messages, but are we sending them unicast? We are not. The hello messages are getting sent multicast to the all OSPF router address of 224.0.0.5. So even though we're on a point-to-point segment, we're still sending these out multicast on 224.0.0.5. So anybody listening, in other words, any router that has an interface connected to us on serial 000, which is going to be router 2, if they're listening for this, then they're going to pick those hello packets up. And we know that router 2 is, because the adjacency is up and it's been formed. So again, every 10 seconds, and I think we've got the debugs on here pretty close, so 37.39 and then 47.48 and change. So from 37.451 to 47.411, right around 10 seconds. Okay, so let's go ahead now and drive on here. We're going to jump onto router 3, and we're going to walk through this a little quick here. So let's go into, from user exec to privilege exec into global config. I'll say router OSPF 1. Now, what do we want to do right away here on, and actually, we'll probably need to do this here on router 2. We'll use the interface serial 010. I'm going to say IP OSPF1 area, actually area 23. Area 23 there, sorry about that. So if I say do show run interface serial 010, what do we see? Well, that's the description is from R2 to R3, and there's my IP OSPF1 area 23. And what that should also show you, this fortuitous failure here where I put in area 0, an interface can only belong to a single area. So you'll notice if I were to say IP OSPF area 24 and then take a look at the interface, it's only going to keep one of those settings, and it's going to be the last one that I put in there, right? Because this interface can't belong to multiple areas. So again, it's only going to keep one of those, IP OSPF1 area 23. So now we've enabled the OSPF process on do show IP OSPF interface brief. We now have OSPF running on loopback 2 serial 000 and 010, right? On router 2. So back over to router 3. So we'll go ahead and mix and match on router 3. This time we're going to activate the loopback address with the network statement 10.1.3.0 0.0.0.255 area 23. And let me get that period in there. Hold on. There we go. And let's go ahead now and drop into the interface serial 010. And I'm going to say IP OSPF1 area 23. And again, the area numbers, and there we go, our adjacency has just popped up, so this is fantastic. Now the area numbers need to match between the two interfaces, or else it's not going to form the OSPF adjacency. So if I were to say do show IP protocols, you can see that the router ID right now is what? Well, it's 192.168.103.1. And why would that be? Exactly. We didn't set the router ID command, right? And we come in here and take a look at all these loopbacks, and what is the highest IP address numerically on any of these loopbacks? It's this guy right here, 103.1, and as a result we end up with 103.1 as the router ID. So we know what to do here. In order to change things, we're going to come in and say router OSPF1. I'm going to say router ID 3.3.3.3. However, the adjacency has already formed, which means when I say do show IP OSPF database, right now it's a little trickier now, right? Because take a look at the information that I have in here. I've got my router ID in here for the type 1 LSA link state ID field, and this is the router ID that I'm being identified by, for router 3, right? Now, I also see some summary type 3 LSAs here. Now you'll notice, where's the network LSA? Why don't we have a network LSA? Exactly, because the network LSA is generated and flooded by whom? By the DR. Takes care of the type 2 LSA, right? So, and it looks like a PR there. That's a DR. So the DR takes care of the type 2 LSAs. Well, are we going to have a DR BDR election here or here? Absolutely not, right? Because these are point-to-point links. So therefore, this is a great example of when you don't see a type 2 LSA. So if you were to be shown this output right here, and this is probably going to be, this is definitely a quiz question. If you were going to be shown this output right here, and the question was, what type of network is between router 2 and router 3, and this was all that you were shown, you could be able to confidently say that it would not be non-broadcast multi-access, it wouldn't be broadcast multi-access, it would be point-to-point, right? Because there is no network link state ID here, so it would be a point-to-point network type. All right, so let's clear the screen there, and we need to resolve some things, right? So I need to say do clear IP OSPF process. We'll say yes. It's going to tear my adjacency down and bring it back up, so that now when I say do show IP OSPF database, my link state ID now reflects something that makes a little bit more sense, a little easier to decipher. And again, remember these type 3 LSAs here, right? This is kind of like distance vector behavior, where the link state ID for the type 3 LSA is what? It is the network ID, right? So we've got the network ID here, but who is my advertising router? So router 3 over here has learned about these type 3 LSAs from router 2. But router 2 is not giving router 3 all the information. Router 2 is providing a topological summary of the area 0 link state IDs, right? Or I should say of the area 0 network IDs, right? So these are all in OSPF 10.1.1.0, 10.1.2.1, 10.1.12.0 over here in area 0. Router 2 is telling router 3. This is why router 2 is seen as the advertising router. So 2 basically sends the summary, right? Because he is an ABR. So he sends the summary, type 3s, into area 23, and router 3 doesn't know what's going on over here in area 0. He just knows that if I want to get to any of these networks here, I'm going to use router 2. And this is distance vector behavior at its best, where router 3 is basically taking routing by rumor, right? That's what we refer to this as, where 2 is telling 3, hey, to get to the 10.1.1.0 or the 10.1.2.1 or the 10.1.12.0, just come to me, right? Although 3 has no idea what this looks like over here. He just has to trust 2 and get the traffic to 2, and then 2 will handle everything. And that's just like EIGRP, right? Where I don't know what the entire topology looks like, but I've got a neighbor and he's telling me that he can get to this network. And that is exactly what we're looking at here with multi-area OSPF, is very specific distance vector-like behavior. I'll put distance vector-like. But don't forget that OSPF is definitely a link state routing protocol. But once we get into multi-area OSPF, we start to see a lot of distance vector-like behavior, and it's interesting. And I'll do a quick segue here. When you take a look at, there's a book out, and I always like to reference these books. We talked about this on Monday night. This book right here is written by John T. Moy. And John Moy is actually the creator of OSPF, and he is the sole author of RFC 2328. You can see right here, he is the sole author of RFC 2328. He created OSPF version 1 as well as version 2. However, this book, and some people have referred to this book as being, basically the RFC. It is not. There is significant information in this book, historical and technical, that really paints a complete picture of not just how they came up with OSPF, but he actually, early on in this book, talks about the need to do a distance vector-like behavior with these summary network link states in order to achieve the scalability that OSPF can achieve, right? And so, again, it's an amazing book. I mean, you could pick a copy up used for $13, it looks like. So I highly recommend this book if you're really looking to dig in and really become a subject matter expert with OSPF. I mean, this is a fantastic place to start. And again, the historical information is absolutely incredible as to why they made the decisions that they made. So again, I highly recommend that book, and highly recommend that you read through the RFC. Now, the RFC is a little long. I think it's 244 pages. Yeah, it's around 244, page 240. So it's about 240 pages, right? However, this is a must-read. There is some phenomenal information in here to help you understand how OSPF works and why it's working, right? Covers a full range of topics. Okay, so we've just reset the the neighbor relationship, the adjacency. Now let's jump into interface loopback 3, and we want to go ahead and make sure that this IP OSPF network is going to be point to point so that it's advertised as its natural /24, which is what we configured it as. So let's see here. So from router 2's perspective, they're asking us to take a look at the do show IP OSPF neighbor. We're going to see that we've got 2 full adjacencies, and both of these are over point-to-point links, right? And the reason we know that is we've got a priority of 0, and there is no DR BDR election taking place, right? And that's what that dash means. It just simply means no DR BDR. In fact, this could be a quiz question output, right? We take a look at this output. You're provided do show IP OSPF neighbor and asked to define what is the network type for the adjacency between router 3 and router 2, or router 1 and router 2. Well, it would be point to point because there's no DR BDR election. All right. So we've got a problem, though. If we take a look over here, you can see that we have area 100 sneaking in on us down here, right? This is area 23, and this is area 0, the backbone area. Now remember, we said that if you have multiple areas, you must have all non-zero areas connected to area 0. However, we do not have that here. So we have area 0, router 2 is my ABR because he sits between areas. That's the area border router. And then we've got area 23, but hanging off of area 23, we have area 100. So area 100 has no connectivity into area 0. So this is going to be a problem. Now, the way we resolve this problem is using virtual links. But first, let's remember that the OSPF hierarchy, right, is you have area 0, and then you have not area 0. And so if this is my backbone area right here, all other areas would need to transit this area. And I think there may be a question later on here that asks why. Why would you need that? Well, it's for loop prevention. Because if I don't have all my traffic transiting area 0, I risk a routing loop. Because area 0 is really what does the sanity check to make sure that all information that's coming in from the ABRs is being checked in area 0, right? Because what we wouldn't want to have is information being exchanged here between area 23 and area 100, and area 0 has no idea what's going on with that traffic. So area 0 needs to know what area 100 looks like, right? So you would need to have a router with an interface in area 0 and area 100 so that area 0 would have all that information and then be able to go ahead and communicate that information to other areas. Now, this is not an ABR here because there is no information being exchanged right now between area 100 and area 23. And let's take a look at that. Excuse me. And let's see what that looks like. So we'll create on router 3, let's see if we say do show IP OSPF interface, and I want to do brief on that. So we've got loopback 3 and we've got the serial interface. Now those are in area 23, right? And this is where it becomes very important. You can see here, area 23. Now, will these show up in area 0? Let's check. Let me come over here. I'll come all the way over to router 1. We'll say do show IP route OSPF. Absolutely, right? Because area 23, does it have a connection into, excuse me, so area 23, is it connected to an ABR that has an interface in area 0? And the answer is absolutely it does. It's got router 2 right here. So as a result, we pick up these inter-area OSPF routes, right? OIA routes. And you can see here the metric is 129 for that one, and it's 128 for this one. And the difference in one being that that is a loopback interface. And remember, the loopbacks have a cost of 1. So the transit network is basically 64 and 64, so 128. And then for me to get to the loopback, I'm sorry, actually the loopback is not shown. So I should probably loop back over here, 10.1.3.0. So for me to get over here, right, is going to be a cost of 1. And that gets added onto that 128, and it gives me 129. But the point being is I am learning, right? We've got type 3 LSAs coming into do show IP OSPF database. I should have type 3 LSAs for every network that the ABR is flooding into area 0, and here they are. There are my network IDs. Who's my advertising router? Well, we know for this one that it's router 3, right? That's who's actually where that's originating from. But here is that distance vector behavior again, where OSPF with the summary link state ID for area 0, right? And the link state ID is going to be the network ID. And this is our type 3 LSA. OSPF is going to fall back onto distance vector behavior and send a topological summary into area 0, basically telling anybody in area 0, hey, just come to 2.2.2.2. He knows how to get over to these network IDs, right? And again, area 0 does not have a full-blown knowledge of what's going on behind the ABR, which is router 2. Okay. So let me clear the screen here, and we're going to go ahead and go over onto router 3, and now we're going to bring into the fold these loopback interfaces we have. Do show IP interface brief. You can see we have all these 192s, 192, 168, 100, 101, 102, 103. So we're going to take the easy way out here. I'm going to say router OSPF 1. I'm going to say network 192.168.100.0, 0.0. And that's going to be 3.255. And I'm doing the net mask in my head. Is that right? 0.3.255. That should be right. I'm pretty sure that is right. Because, and I don't want to have to do the whole summary out here for you. Oops, sorry. Or get the whole net mask out here for you. So if we were to summarize that, so that's sort of the interesting low order bits that are in this octet 0, 1, 2, and 3. So if I were to say 0 and then 1 and then 2 and then 3, I'm sorry, 2 would be 1, 0. It would be there that they no longer match up, these last 2 bits, and so we would be at a, it would be a, well, actually not a 30 because it's not in the last octet. But it's going to be, what are we looking at? 24 to be 22, and the 22 should be 255, 255, 252. So that's correct. Yeah, 252. So I'm going to work that out a little quick there. All right. So there we go. So we've got that correct. And then we're going to say area 100 is what we're going to use. Again, referring to the diagram we have on the right-hand side over there. Area 100 is where all of these loopback interfaces are going to live. Right? So we've just activated, if I say do show IP OSPF interface brief, so take a look at this. We've got a lot of interfaces here in area 23. However, we also now have these interfaces in area 100. So let's come to router 2 and say do show IP OSPF, or do show IP route OSPF. And my question to you is, how come those loopback interfaces don't show up here? Where are they? Where are the 192 loopbacks? We've enabled OSPF. They have OSPF running on each of those interfaces. Why is it not being advertised over here to router 2? And again, it's because we have no connectivity from area 100 to area 0. It does not exist. And so this router will not be acting as an ABR, because again, by definition, what is an ABR? By definition, an area border router has at least one interface in area 0 and at least one interface in a non-area 0 area. So does he meet the criteria? He does not meet the criteria as an ABR, because where is his area 0 interface? It's not here. And if it's not there, then this is not going to be an ABR. And if it's not an ABR, is he going to flood a type 3 LSA for all these 192s into area 23? Absolutely not. It's not going to happen, right? So that's the problem that we're faced with. Excuse me. And so let's go ahead and finish up on router 3 here. Let's finish our config where we're going to change all of the loopbacks to point-to-point. So, whoops. So interface loopback 100. We're going to say IP OSPF network and point-to-point. And then interface loopback 101. And that is not what we wanted. Interface loopback 101. And we'll say point-to-point, and then interface loopback 102. Point-to-point, and interface loopback 103. Point-to-point. And the reason we're doing this is because it's going to advertise them as a point-to-point network type, and that will, excuse me, that will preserve their naturally configured subnet mask, which was a /24. And I'll go back. We'll change one of them after we get the virtual link worked out. Excuse me. So that you can see that it'll advertise it as a /32 if we don't do that. So now we come upon our first question here. It says, what would happen if routes could pass between areas without going through the backbone? And we talked about that a little bit over here in the drawing, right? So if these routes, if these loopbacks were allowed to get dumped into area 23 without first having to go through area 0, what problem could that cause? Well, it could cause a routing loop. Because again, forcing all of the traffic to have to go through the backbone ensures that we get the type 3 LSAs generated. If we don't do that, then we're not going to get those type 3s. In fact, we've already seen that this will not be an ABR, right? Because it does not have an interface in area 0. So again, we could end up in a situation where we've got a loop. So how do we solve this problem? So this can sometimes become a common problem if you're merging with another company, if you're merging departments, right? Maybe you've got the math department had their own setup and they want to connect their OSPF network into the college network somewhere, and they don't have connectivity to area 0. You know, maybe you got to run fiber or something like that. But again, how do we solve this issue? And we're basically going to solve it using a virtual link. Now, a very important note about virtual links. While it will resolve this issue, a virtual link is not something that you design your OSPF network around. In other words, what I'm trying to say is, when you're designing your network, you shouldn't be picking OSPF area numbers because they're cool or they're your favorite number, and not connecting things into the backbone area and simply saying, well, no, we'll just throw virtual links everywhere and that solves the problem. And it will solve the problem until something breaks, and then troubleshooting turns into an absolute catastrophe, right? Virtual links really make troubleshooting difficult from a number of perspectives. Okay, so let's go ahead now. Let's get this virtual link configured between router 2 and router 3. Now, the key with the virtual link is that we do it through the transit area that is connected to area 0, or to the ABR that has a connection in area 0. And when we look at our setup here, the transit area, right, is going to be area 23. So who are the two routers here where we can use these routers? Because basically, if you think about it, a virtual link, and that's not going to be a good color choice, I don't think. So a virtual link is nothing more than, think of it like a GRE tunnel, right? So the virtual link is like a tunnel. This is my virtual link. And it just allows me to extend area 0 through the virtual link to the router where we've got the discontiguous areas, right? And so I'm going to be able to extend area 0 through this virtual link tunnel from router 2 down to router 3 so that these networks here that are on router 3 will now be able to communicate, excuse me, because their area, area 100, will now be seen as if it is connected to area 0 through that virtual link tunnel that we're going to create in the OSPF area 23 transit area. So how do we do the virtual link? It's actually very simple. Excuse me. And again, it's all based on router IDs. Okay. Again, if it's not sinking in yet, that router ID in OSPF is absolutely critical. In EIGRP, when we talked about it, it was under the context of, well, hey, if EIGRP has an external route coming in, that the router ID is going to help us identify the originator. And that was pretty much it for the router ID with EIGRP. With OSPF, it is significantly more important. And it is from end to end with a link state database. The router ID is critical. So how are we going to do this? Let's go ahead on router 3. We're going to go into router OSPF 1. And it's a very straightforward command. So what area is my transit area going to be for my virtual link? Well, it's going to be area 23, right? So I say area 23 virtual link. And on router 3, who's the ABR on the other side of this virtual link in area 23 who's got the area 0 connection as well? Well, we know it's router 2. And his router ID is 2.2.2.2. So I say area 23 virtual link 2.2.2.2. Now, you'll notice nothing's happening here if I say do show IP OSPF interfaces. And I want to do the brief on that. You can see that here we now have this VL0, right? And let's talk about this for a second. So we've got this virtual link 0 here. And let's get the pen back over here. We've got this virtual link 0 here. Process ID, right? It's router OSPF 1. And what area, you'll notice we didn't say, when I ran that command, area 23 virtual link 2.2.2.2, did I ever say area 0? I did not. In fact, I said area 23 because that's the transit area we're going through. However, the virtual link serves one purpose and one purpose only, and that is to basically pin down a tunnel through a transit area and to extend area 0 from this ABR down to this router, right? And so the virtual link will sit in area 0. And that's how it drags area 0 down here, excuse me, to router 3. Now, another interesting fact, how does it come up with the cost? Well, the virtual link is going to inherit the cost of the transit link that it has to go through, right? Or links that it has to go through. So here my cost is 64 because that's the same cost of the transit link between router 2 and router 3. So I've got the virtual link here. However, if I come over all the way to router 1 and I say, do show IP OSPF database, I still don't have any of those 192s because I need to configure the ABR. And here we go. This is fantastic, right? So take a look. We're getting all kinds of mismatched area ID messages here that are scrolling. And this is actually another good quiz question. Why would you receive this error? So you would receive this error because we have a virtual link down on router 3 pointing to this guy, router 2. He's pointing to me, remembering, right, I'm 2.2.2.2. That's who the virtual link is pointing to from router 3. However, it says where are we at here? Mismatch area ID from backbone area must be virtual link, but not found from 10.1.23.3, which means there's no virtual link that has been configured on the router 2 side. So let's go ahead, we'll clear the screen here, and let's resolve this issue right now and say router OSPF 1, and we're going to say area 23, right? Because that's the transit area in which this ABR sits, through which we need to extend area 0 down to router 3 so that all those loopbacks in area 100 can participate. Virtual link, and who is the router ID at the other end? 3.3.3.3, and there you go. So take a look at that. So it's really extended the area 0 adjacency, right? This is the same message we get when an adjacency comes up with neighbor 3.3.3.3 on OSPF Virtual Link 0. It has gone from loading to full. So now that we've got this done, let's take a look and see what our do show IP OSPF database looks like now. So very interesting, right? And I'm on the ABR. In fact, let me step over to this guy, router 1, and let's take a look at router 1 first before we dive into router 2. So we've got some very interesting information here. So remember, router 1 is only in area 0. So these are my type 1 LSAs, my router LSAs. The link state ID column here is the router ID, as well as the advertising router field is the router ID. So who am I getting a type 1 LSA from? Take a look at that. So this shows you right here that area 0 has been extended through this tunnel all the way down to router 3, because we know that the type 1 LSA has what kind of a scope? Type 1 LSA is area local scope. And what that means is the type 1 LSAs do not show up across areas. So then how is it that router 3 is giving me a type 1 LSA identifying himself? Because area 23 sits between router 3 and router 1. And I should say area 0 over here. Well, again, we have extended area 0 with the virtual link down to router 3. So that virtual link is making router 3 appear as if he is legitimately in area 0. And that is, and I apologize, it's getting a little messy there, and that is validated right here by the show IP OSPF output, because I've got a type 1 LSA that says, hey, router 3, I'm in this area. Now, the age, very interesting here, right? Let's take a look at that. Age is 2, and this is seconds, 334 seconds and 41 seconds. Let me clear the screen. Let's run that command again. What are the ages now? So that one changed, and that one changed. What happened to this guy? He did not change, did he? And the reason that he didn't change is what we see right there. The DNA, excuse me, which stands for do not age. Now, the story behind, I shouldn't say the story behind this, the technical reason as to why the do not age bit is set for this type 1 LSA, right? Remember, every 30 minutes the LSAs get reflooded, whether there's been changes or not. After 60 minutes, the LSAs age out. That is the max age time. Why would you think that this LSA here, this type 1 LSA for router 3, why would you think it would have do not age set? Well, it's because it's coming from a virtual link. And virtual links are demand circuits, or they were back in the day, right? And they still are today. They're still demand circuits today. And I should rephrase that by saying that the use case for these back in the day, and we'll take a look at RFC 1793 here in a second, that actually John Moy also wrote, that addresses the demand circuit need, is that we've got this virtual link where we're extending area 0 way down here to router 3. Now there could be, let's say that we had a whole bunch of routers in between here. And each of these routers is running circuits where we're paying the provider based off of the usage, whether it's time or bytes that are passing through. We don't want a virtual link that runs across all of these routers running up excessive fees and charges if we're paying for these links by usage. Now, nowadays, that's probably not the most popular use case anymore, but it used to be back in the 90s, right, in the early 2000s, where you would have circuits that you were using and you were paying for those circuits based off the usage. And the virtual link, right, where you've got all kinds of flooding that would take place from area 0. Again, because remember, we're extending area 0. And if we're going through a whole bunch of routers that have circuits that we might be paying for on a per usage basis, then we only want that traffic coming through when it's demanded, right? Or when it's needed. And that's why we call virtual links demand circuits. And that's also why we do not age those LSAs. We don't want those LSAs flooding back out every 30 minutes. So we put it into the routing table. We put it into the OSPF database. And here is where it will sit permanently, because do not age is going to be set. And let's take a look down here. There's the DNA output on 10130. Now we're looking at type 3 LSAs down here, right? These are type 3 link state advertisements. These are the summary network link states. And again, I'm on router 1, right? And who does router 1 see as the advertising router here? Well, he sees it as router 3, because remember, router 3 is originating all of these networks, right? And router 1 knows that it's router 3 because, again, we've picked up a summary from area 100, because now area 100 thinks it's connected into area 0 because of the virtual link. So now we get the type 3 LSAs, and now we get that, again, that distance vector behavior where router 1 says, yeah, all I know is that to get to that network, I need to go to router 3, identified by the router ID 3.3.3.3. And everything associated with router 3, and let me correct that, everything associated with area 100 across the virtual link that terminates at router 3, I'll make sure I make that distinction. So everything associated with area 100 coming across the virtual link will have the do not age bit set. And we already talked about why it's going to have that set, because the OSPF virtual link is looked at as a demand circuit. And so that kind of leads us to another really, really informative RFC here from 1995, and it actually points it out right here. So while mainly intended for use with cost-conscious network links such as ISDN and X25 and dial-up, and these were services back in the day where you would have to pay by usage. So the modifications in this memo may also prove useful over bandwidth-limited networks, such as very slow links, leased lines, and packet radio, right? Because again, the title of this RFC is Extending OSPF to Support Demand Circuits. And if we come down to the table of contents here, you'll see where it talks about virtual link support, right? Flooding over demand circuits. And if we go down to area 3.4, and let me see if it's going to jump for me. I think that just did. Let's make sure here. 3.3. So here we go. So virtual link support. So OSPF virtual links are essentially unnumbered point-to-point links. Accordingly, demand circuit support for virtual links resembles that described for point-to-point links in the previous section where they were talking about it. So again, The virtual link is a demand circuit, right? It's going to behave just like a demand circuit, and to ensure that you don't have excessive flooding of all of this information across what could be, per usage circuits, you have your do not age bit set. And so that is how you configure the virtual link, right? We've seen how we've been able to extend the virtual link, or to extend area 0 down to router 3 so that area 100 can participate. So let's jump on to router 2 here, and let's say do show IP OSPF neighbor. And you can see that we now have another statement here for 3.3.3.3. And it's that virtual link statement. And why is there no dead time? Because it's not going to age out. This is a virtual link. And that is the interface, OSPF VL0. If I added another one, it would be VL1, and then VL2, and so forth and so on. All right, let's do a let's say do show IP OSPF interface. And there is the virtual link, and let's talk about this for a second. So we can see here that the virtual link is up, and so it says attached via, I've always thought this was funny, attached via not attached, right? So it's attached via, it's not attached. So this just simply means that it's a virtual link, and we haven't attached it, because what do we typically see here? It's either a network statement, right, or it was done under the interface. Here it is not attached. What is my cost? Well, I'm assuming the cost of the link I'm going over, or links I'm going over. So here it's 64 because it's a T1. And what is the network type? Virtual underscore link, right? So again, we see here that we've got this virtual underscore link, and the state of that link is point to point. It assumes the hello, dead, and wait time intervals of the interface that it's going over as well. Okay, and the neighbor count is 1. It's adjacent with neighbor 3. And what else are we seeing here? And we're going to see the other interfaces now. All right, so that's what we were interested in, right? Is taking a look at that virtual link. Now, the next question we get is, why are virtual links useful? Well, they're useful in scenarios where you end up in a situation like this, where you just, for whatever reason, end up with an OSPF area that is not connected to area 0, that's hanging off of a router that does have connectivity up to an ABR who does have connectivity into area 0. And again, remember, by definition, that's going to be true because an ABR has to have, by definition, one interface in area 0 and one interface in any non-area 0 area. That is an ABR. And so again, this is a temporary mechanism. You should not be designing networks with virtual links in mind. When you're designing your networks, you should be making sure that you've got a solid, and when you're doing multi-area OSPF, right, you have a solid multi-area OSPF configuration. I've actually seen a couple instances where the OSPF was configured and they wanted to be cute, and they started out with OSPF area 51. Well, that's great until you want to add in another OSPF area number that's not going to be 0, because you can't have area 51 connected to area 99, right? That's not going to work. We just saw what happens down here when area 100 is connected to area 23, right? Is this going to fire itself up as an ABR and say, yep, great, let's fire in these type 3s this way, we'll fire in type 3s that way, and we're good to go? No, it is not, because it's not going to act like router 3 is not going to behave like an ABR because he is missing the interface into area 0, right? So the virtual link solved our problem here. Looking at this diagram, how else could we have solved that issue without using a virtual link? Absolutely. I could have simply said, and we'll switch over to blue here, I'm going to take my, and let's say this is serial 0, interface right here, and let's run a point-to-point connection here to this guy's serial. Well, actually, he's using serial 010, so we'll say serial 020 and put it in area 0. And that would have solved the problem as well. But again, what we're looking at here is a use case where that is not possible. Okay? All right, and so again, the virtual links are useful. They're temporary. It's going to help us pull down and pin down area 0 down here onto router 3 so that area 100 can transit through that virtual link tunnel and participate in the OSPF routing domain. And again, why are virtual links a poor long-term decision? The number one reason, without a doubt, is troubleshooting. It becomes extremely difficult. Step 4. All right, so for step 4, we're going to talk about summarizing an area. But we're not talking about summarizing topology information. We're talking now about summarizing routing information, right? So we're talking about summarizing routing information here, which is it's got to lead us right down here to these 192.168s. This is screaming, somebody come down here and do some summarization. All right, so step 4 says loopbacks 100 through 103 can be summarized into one supernet, and we've already got the /22. We already worked that out. So the 255.255.252.0. Whoops, .0. And we're going to go ahead and do this on router 3. So let's jump down to router 3, and let's get the summarization configured. So how do we configure a summary where with EIGRP we would go, remember we went down to the interface with EIGRP and we would say, interface, and this would be serial 010, and I would say IP, summary address, EIGRP 100, and then I would have said 192.168.100.0, and then put in 255.255.252.0, and then I could have thrown a leak map in as well, right? And I would have hit enter. Now, that would have done the summary in EIGRP, because remember, EIGRP distance vector, I can summarize anywhere. Anywhere I want to summarize, I can do that summary, right? Now, with OSPF, it is very, very different. You can only summarize at an ABR or an ASBR. And the reason for this is that, remember, that link state database is critical in OSPF's functionality. So what I cannot do is just go into the middle of area 0 somewhere and decide, well, I'm going to start summarizing addresses here in the middle of area 0 in the hopes that these other routers figure it out. You can't do that, right? It has to be at an ABR or an ASBR, and again, the ASBR we would be summarizing external routing information. At the ABR, we're summarizing OSPF routing information in the OSPF routing domain, which is what we're going to be doing here. So again, I can leave that on there. It's not going to harm anything, but we'll take it off just for clarity. So now remember, you have to do the summary at the ABR. So how can I do that on router 3? Well, remember, that virtual link that we pulled down from router 2 now has router 3 do show IP protocol. Now has router 3, or do show IP OSPF. And I know it's going to say it in here. So what I'm looking for in this, and I'm looking for, it should say in here, router is an ABR. If I'm looking, I think I may be looking in the wrong place. I haven't checked to see. Oh, here it is. It is. There we go. It is an area border router. And I apologize. I was looking for this in another video, and I knew I had the right command, and I just did not see it. So here it is. So show IP OSPF will tell you what that router is, and it thinks it is an ABR. And the reason it thinks it's an ABR is because we have that virtual link. So let's do this, right, to prove that. If I go back into router OSPF 1 and I say no, area 23, virtual link 2.2.2.2, right? The adjacency's gone. Okay, so if I come over to router 1 now and I expect to see the same database, what do you think I'm going to see? Well, we're going to see it actually, because we're going to have to wait for it to update. And since those are not going to age, if I were to say do clear IP OSPF proc, let's clean this out of here right now. So this will tear my adjacency down, right, with router 2. Now let's take a look at the database. Now, well, they're still there. And they should not be there. I'm wondering if we would have to wait for these to actually age out. And that's an interesting question. So the do not age bit is set, right? So how are these eventually going to go away? Maybe we come to the other side here. Do clear IP OSPF proc. Let's see what happens. Come back over to router 1. And maybe you just had to tear down both sides of the virtual link. No, they are still there. And so this is definitely one of those instances where you could make it much more difficult on yourself trying to troubleshoot, because I'm seeing this information in here, but we know the virtual link is broken. If I were to say do ping 192.168.101.1, do I have any reachability? I don't, right? Because although it tells me the advertising router is 3.3.3.3, that router is no longer in area 0, right? And so these routes are no longer valid routes. So, and I apologize there, I want to do that again. So here's what we're going to do. I'm going to say repeat 2222. We'll throw it in there and let that run while we come back over here. So I pulled it out, right? So now what happens if I say do show IP OSPF? Does it say it is area border router here? It does not. At least I don't see it. Let me double check. Yeah, it does not, and it shouldn't say it, right? Because again, router 3 is not going to think he's an area border router if there's no virtual link there. It's just not going to happen. So let's go ahead. Let's add our virtual link back in. Let's pull this back together. So we'll stitch that virtual link between router 2 and router 3. And we should see that we're going to have an adjacency come up, and there it is. And again, you can see it incrementally created that OSPF VL, because if I say, let's say Control U, do show IP OSPF interface, and want brief, I apologize there, brief, you can see that we now have virtual link 1. Virtual link 0 is gone. But let's come back over to router 1. And do we have connectivity now that the virtual link is back? We do, right? And that's the key. That virtual link has to be there, right? To stitch area 0 from router 2 down to router 3, to bridge that gap through the area 23 transit area so that area 100 thinks that he's, connected to a router that's connected to area 0. Because now when I say do show IP OSPF, is it an area border router? Yes, it is an area border router now. And so that's how you can tell that the virtual link is doing what it's supposed to do. And again, of course, it's always nice. We've got this full reachability here. All right, so now back onto router 1, and I would have thought this would be done by now. There's about 22,000 of them there. All right, so if I were to say do show IP route, and I apologize because we're not going to have the, you can see here, I guess this will be our before shot, right? So here are the 4 routes right here. These are the loopbacks, right? We're learning about them as inter-area routes because they're coming from area 100. And again, 64 and 64 is 128, and then the hop to the loopback is going to be 1. So my cost for all of these is going to be 129. Okay, so we're going to do a summary here. And remember, we have to do the summary on the ABR. And that's where I was at before I ran off on the the tangent there of showing how you can tell that the router is an area border router. All right, so we're going to now go ahead and configure the area range command. So now this gets done under the OSPF global configuration section that we're in when I say router OSPF1. So I want to say area, and what area am I doing the summary for? Well, I'm doing it for area 100. So I say area 100 range, and we already know it's 192.168.100.0, and then my subnet mask, 252.0, right? And again, when you're doing your summarization in OSPF, it has to be at the area border router for your internal domain routing, or at the ASBR for the external routing information. And now if we were to transition back over to router 1 and run this show IP route command again, what would we expect to see? Absolutely. We see that we've got an OSPF inter-area route to the 192.168.100.0/22. So if I come back and say do ping 192.168.100.1, we're good. What about 101.1? We're good. 102. And last but not least, 103. So we've got full connectivity there from router 2. Let's take a look at the do show IP OSPF database on router 2. And what do I see here? So we definitely cleaned up the OSPF database from an LSA perspective, right? Because am I seeing LSAs for every single loopback address in the 192.168 range? I'm not. I'm now only seeing the summary. And so here again, this is my type 3 LSA as router 2 sees it in area 0. And the same thing, the type 3 LSA for the summary network link state in area 23, right? So, because remember, these are all coming from area 100. They're all coming from area 100, so they're going to be seen as summary network link states, type 3 LSAs. And again, all we're seeing is that summary. So if I needed to get more information about that summary, right? Because I have the network, right? Here's the network that we're looking at, but I don't have the subnet mask. If I wanted to get that subnet mask, I could say do show IP OSPF database summary, and now this is going to give me additional information about the summaries that I'm learning. And specifically, we're going to troll down here and hopefully eventually hit, yep, there you go. So we take a look at the specific command, which was show IP OSPF database summary. Now, it's not showing me a summary of the database. It's showing me the type 3 LSAs, which are summary LSAs. So this isn't trying to summarize the database. It's showing me the type 3 LSAs. And take a look here. What do we have? Bingo. Whoops. We have the /22 mask, right, for our summary. And that is my summary network number, right? So we've created that summary. We've got the summary network number that's showing up on router 2 and router 1. The final thing we'll take a look at is just like OSPF. If I were to say do show IP route OSPF, you're going to see that we've got a special entry here, again, identical to EIGRP, to null 0, right? And what this means is null 0 is the bit bucket. Very old Unix term. And what this means is if I have traffic, because remember, we're down here, we're saying, hey, we know how to get to router 3. I know how to get to all the networks that are included in 192.168.100.0/22. Now, if there was a network inside this range that we did not have an actual network for or a route for, that traffic could possibly loop in the network. However, the null 0 interface ensures that that does not happen. So the next question we get actually addresses that. It says, what does the next question ask? It looks like the next question is kind of cut off from the lab, and it actually refers to the bit bucket. It says this behavior is known as sending, oh, there it is. This behavior is known as sending unknown traffic to the bit bucket. It means if a router is advertising the summary route, receives a packet destined for something that the summary covers, but that it doesn't actually have a route in its routing table for that network, it's just simply going to drop it. That way the traffic doesn't loop around the network. And so it's, what is the reasoning behind this behavior? Well, again, remember, the reasoning behind the behavior is we want to avoid loops in our networks, right? And this null zero interface that gets installed auto-magically into the routing table makes that happen for us. All right, so let's go to step 5 now. Step 5 is actually asking us, it's saying, hey, let's create that default route on router 2. So we'll step over to router 2 here. And I'm going to say router OSPF 1, and I'm going to say default information originate, and now you'll notice I can set a metric and I can use the always keyword here. Now typically when you do default information originate, you have a default route defined, a static default route defined with the IP route statement. However, if you use the always keyword, you do not need to have that default route defined. And in fact, that's what we're going to do here. It's asking us to put in default information originate always. And now if I say do show IP route, you'll see that we're going to have an OE2. And let me make sure I did, oops, sorry, did that backwards. Put the default route on the wrong location. So on router 1, we're going to go into router OSPF 1, and I'm going to say default information originate always. So router 1 is going to flood a type 5 LSA, right? It's being redistributed into OSPF as a type 5 LSA. So if I say do show IP route OSPF on router 2, now we see this default route right here, this OE2 default route, right? And it's an external type 2 because that is the default. Now, this is being learned from who? It's being learned from router 1. Well, let's go over and take a look at router 3. And let's see, do show IP route OSPF. And router 3 is actually learning the default route, and it's learning it from router, from router 23, from the 10.1.23.2, which is the interface on router 2. So it's learning it from router 2, right? Okay, so the next thing that we're being asked to do here, it says you should be able to ping the interface connecting to the internet from R2 or R3 despite never being advertised into OSPF. And that's correct, right? Because I have a default route on R2 and R3 that says, hey, go ahead and send your traffic to R1, all traffic that you don't have a more specific match for. So if I say do ping 172.30.30, and is it 1.30.31? So I've got connectivity from R3, and if I've got connectivity from R3, I definitely have connectivity from R2. And so I've been able to ping both ways. All right, so we've established the full connectivity. We've looked at the default information originate always. We took a deep dive on the virtual links. We actually got to take a look at the John Moy book, which I highly recommend if you've got $15 to get yourself a copy, used on Amazon. You can download the RFC 2328 on OSPF. We also took a look at RFC 1793, which John Moy also wrote, that talked about the on-demand circuit support, or extending OSPF to support demand circuits. And we saw that that's really what the virtual route is behaving like. And that's why that do not age bit, oops, sorry, I'm on a router that we're not even using there. And that's why that do not age bit, that DNA bit that we saw, let's see if we can get that back right here, right? That DNA bit is going to be set for information that we're learning over that virtual link, because we only want information flooded over that link when it's absolutely necessary. And so it will not age out. Okay? All right, well, this wraps up Lab 3-1, and I will see all of you on Monday. Enjoy the rest of your weekend.